Okay, good afternoon, everyone. Welcome to this week's episode of Graph Guy. As always, I'm Clark Ritchie, and I'm the Graph Guy. Uh, so, a few little housekeeping items as usual. We do have Puppy Cam mostly back online. So, if we get some puppy action going on, we can maybe get a shot of the dogs. It's got a weird blue tint to the camera, so it's back online, but there's something strange happening with color. I'm not 100% sure why. We've got some quiet, but there they go again. Okay, they're gone. Might have had some early puppy cam. Um, so we may get those visitors. Um, Also, as you can see, we still do have a big push for some more subscribers. We're getting very close to our goal of my goal of 20 followers or subscribers. Uh, Really help me, please, show both my teenage now daughters that Dad really can have a stream that more than a handful of people will subscribe to. Don't know if that'll get me over the cool hump, but it certainly can't hurt. Uh, and we have if those of you didn't see it last week we had Dr. Weidong Yang on, founder and CEO of Kinniviz. We had a great talk with him. He was our first ever guest on Graph Guy, and information about that show is up on our website. So you can get it there, as well as links to the video and links to some of the information about what Kinniviz is doing that we talked about last time as well. All right, so without further ado, let's get into today's topic. So today I just wanted to talk a little bit about scaling your graph database. And let's switch over here. And so, I feel a little like Bob the Builder here. Like, can we build it? Yes, we can. Um, I've been working, as you know, in this graph database space for, gosh, probably about 8 years now. And I still pretty consistently hear people talking about being concerned that they can't scale the graph database. I'll hear people say, "Oh, I tried it, and once I got to like 30,000 nodes, someone told me once, it just didn't perform anymore." Or, I'm concerned it won't scale. Um, I tried it; it was really, really slow at scale. You hear a variety of these things, and this is true, I think, for a lot of databases. Um, I'm obviously going to be giving you some very specific tips for Graph, in particular for Neo4j, because if you've been following the show, that's really the primary graph database that we're working with here. We've talked about others. Uh, so some very specific tips for making sure your Neo instance scales. But a lot of what I'm going to talk about can be applied to other database types as well. So what you're looking at here is that we're chatting a little bit, because I do want to prove that you can scale. This is the Neo browser, clearly. And I've got the system info for database up and running here, and it's auto refreshing, so you can see that it's live. This is an actual customer database, which is one of the reasons why you can't see the URL or anything. So we keep that all private, and you can't see any data. Um, but what you can see here is we're at 2.3 billion with a B nodes, over 5, again with a B, billion properties, and over 2 billion relationships. And they're just updated for us, because as you can see, this is currently loading data. So we see that peak transactions, there were 98 concurrently. There's currently two writes and a read going on, and so on and so forth. And this is about 1.1 terabytes at the moment in store. Database is about 879 of that. So I just want to have this up here so you can see I'm not kidding. This is a production database. This is a lot of data. It's not the largest one I've run. It's the largest one I can sort of give you a glimpse at for the moment. So you absolutely can get there. The database does scale. There, it updated it again. And you can see this database has been running actually for quite some time as well. So let's talk about some ways to make sure you can get to scale. And it's probably obvious, but the first thing I talk about is testing. And this is also probably one of the hardest things to do well. And believe me, as someone who writes a product that is designed to run on top of a graph database commercially, I am well aware of the challenges inherent in this. Glad somebody loves the background too. Thank you. That's our new Discovery Bridge from the new Star Trek Discovery. Love trying to play with backgrounds since we're all constantly on video chats and things now. So, but thank you for that. Testing is hard, right? So there's two aspects of testing, right? If you're developing a database or any kind of system that uses it, you of course want to make sure that your queries are correct, right? We want to run the right queries to get the right data. That's clearly important. If that doesn't work, none of the rest matters. Being wrong at scale is worse than being wrong at small scale. But the trap we can fall into is developing an analytic, even a simple query sometimes, running it with a little bit of test data because we want to know that it works, right? So very often when we're developing these analytics, we want to make sure they work. We have a very small set of test data so that we know in that test data this pattern, for example, occurs, and we need to be able to find it. And so we typically develop small amounts of data to find that, right? Developing large sets of data that we can test with can be very tricky, it can be hard to do. And so we run that analytic and it runs fine, and we assume, well, it's running fine now. It always works. I always get the right results, which is correct. It must be good to go into production. And of course, the challenge in production is there tends to be a lot more data. And I've seen it many, many times. That query now in production doesn't run well, or maybe even at all, depending upon how big your database is and how complex that query is and how significant the problems with it might be. So, that really means that we have to find ways to test the database at scale, whether that's using real data, if you can get it right. Real data is always the best. Or pulling in some other data sources, mocking up data. There are tools that let you create mock data, but whatever you can do, I really can't stress enough the importance of not using the production environment as essentially QA for scale. And I'm not saying I haven't been guilty of it a time or two in the past. I think we all have, but that can be highly problematic, right? So why are things harder at scale, particularly sometimes in graph? And to be clear, before we even go into that, there are some things that graph actually does really, really well at scale, better than, say, relational databases. What do I mean by that? One of the challenges, and we may have talked about this in an early episode, with relational databases, and again, simplifying somewhat because, yes, you can tune consistency behaviors for different relational databases in different ways and so on. But generally speaking, if you've got a system that is constantly ingesting data and you need to run queries at the same time, that can be very, very challenging in a relational scenario. Why? Because as you're inserting data into a table, typically the relational database is going to lock the table in order to perform that insert or that update. And the table's locked, again, under typical consistency rules, that will block reads to ensure you don't get what's called a dirty read, essentially, right? So a read of data that is really essentially old because the commit or the update that is happening might be in the process of changing that data. So that can block. And I've seen situations in the government in particular, where we have very, very large systems, that there's, that sounds like a puppy cam alert. All right, puppy cam alert. Okay, and there's one big boy, and he doesn't like something out the window. And here comes the other one. Oh, and now we have two puppies. Okay, yep. So there they go, and there they go to see Mama. Alrighty. I don't know why the blue filter, but puppy cam. So yeah, in those scenarios, I've seen relational databases essentially come to a halt in terms of being able to query them because there's so much ingest happening. you just can't query them. With a graph database, you don't run into that problem because what if I insert, say, a customer or an updated customer, I'm only locking that one particular node that I'm creating or updating, and I can query across all of the other customers. Odds are pretty good that that one thing I'm updating or inserting is not necessarily affected by that query that I'm running. Or even if it is, it's going to be the amount of time that that particular lock is held for the update or the create is very, very short, right? I don't have to lock that. I don't have to lock all customer nodes whenever I create a new customer or update a customer. I just have to lock that particular one. So at scale, in certain types of performance scenarios, you can actually get really, really significant performance benefits with a well-run graph database. But let's talk again about some specific ways that things can go wrong at scale. So let me get rid of this tab. So one of the when I used to work at a different I used to work at another database, or rather at a database company called MarkLogic that's still in existence. They ran a document database, and when had a lot of XML under the covers. And we used to have a joke when I worked at MarkLogic, which was if something was going wrong with the query, you'd always blame. There's always a problem with namespaces. And those of you who are to work with XML, you probably nod your head. Yeah, namespaces can be a challenge. Well, I'm going to tell you that if you're having a performance problem with your graph database, the problem is probably indexes. So let's look at that in a second. Let's look at that now. Before we do, I wanted to show you a little bit about what kind of data I actually have in this database. This is just, again, this is essentially a graphical view of that model. Again, this is, you've probably seen this tool before. This is actually a tool our company puts out. That I'm not here to demo to you, but I do want something where I can show you the model that's in the database really nicely. And so I've created a database with a handful of data. I've got customers that have phones and emails and they live someplace and they purchase products through transactions that have line items and so forth. So I've loaded up a handful of this data. So if I see how big my database is, this is my local one. I can just say, hey, match n count. Sorry, return count n, and I can see I've got about 4,000. So it's tiny. It's a tiny little database. Wasn't going to try to replicate something monstrous here to show you. So I can pull a customer, right? So I can say match C. I can type today. C colon customer. Return C limit 1. So let's pull back one customer. Whoopsie. So let's make it a little bigger for people to see too. Okay, very good. So here's a customer. Let me see. Customers have a first name, and they've got this CID property here, and some have others properties as well. So really simple, and it runs really fast, right? So that's fun. So let's do a query now. And I hate it when full screen does this to me. Go away. All right. Enough full screen then. So let's essentially take that last query we wrote, and let's just add a where clause. So now I'm going to use the more expansive Cypher syntax just for sort of readability here. So C dot CID equals let's try 2D2. Okay, so I get back one node, and that is the right CID, and it works great, right? And it seems like it's probably fast. So this is me testing right on a small amount of data. And I say, well, that's a good query. So I can probably ship that into production. And then let's run another query. Whoopsie, that's not the query we want to run. Let's take this. Let's change it up a little bit. And let's say where C dot first name equals Clark. And I don't need the limit on there. I didn't really need it before. All right, so it comes back. Let's get rid of the limit here so you can see that that still works the same way. Here we have two customers. They're both in the same CID. One's got some additional data as well. Lovely. It comes back really fast, right? So we ran that; it was super fast. So I could say, like, yeah, this looks like I could totally run this at production scale as well, no problem, right? Um, However, there is a problem, right? And this is again a case where I'm not testing at scale, so all my queries are not only correct in this case, but they're super fast. I've only got 4,000 nodes. It's no problem. If instead I had 4 billion nodes, this last query here would be a really big problem. How do I know that? Let's look at something available in Neo, and we're going to use explain. There are two keywords here that are similar. There's explain, and then there's profile. We'll actually go ahead and do profile. Explain does kind of, let's do explain. Explain essentially tells you, or gives you some insight into how the database is going to plan the query. What's it going to do when we run this query? What is its plan of attack for, in this case, parsing out that cipher and going and getting the data? Explain doesn't actually run the query. It just tells you what would likely have happened if it had run the query. And I say likely because it can be a little bit different when you run it. Profile, on the other hand, actually runs the query, but also gives you the query plan. So profile, you're guaranteed to see exactly how the database did execute that query, which can be a little bit different, again, particularly in complex queries on large databases, than explain, because as it gets into it, as you'll see in your explain, there are some estimates, whereas profile, you'll see actual numbers. And if those estimates differ from someone's actual numbers, the query plan could differ slightly. But explain is a great way to start looking at your queries. So if I run this, let's make this full screen and see if I can make it a little bit bigger for everyone. Lovely. We'll see what Neo is going to do. Now, I am not, in this particular episode, going to try to do a deep dive on everything that can possibly come back in an explain. It's a pretty complex topic. It's certainly more than a half hour here. And in reality, it's something that I will probably bring someone much more expert on that in to talk about, because this does get pretty deep into the guts of the database. And it is important if you really want to do some query optimization sometimes. But what we're doing now, we're going to look at some basic things. So what's the first thing it does? It does what's called a node by label scan. Node by label scan means it's going to go find all of the nodes in the database that have the label that I'm asking for. So it's telling us that the variable that's being worked on here is C from my query, and then it's going to go for customers. So it goes and finds every single customer in the database. Now, and it tells you again, here's the estimation. It estimates there's probably about 847 customers in the database. So again, small scale here, no problem to go and get 847 things out of the database. And then there's a filter, right? Because I said I want only the customers that have a first name equal to Clark. And so here, that's what it's doing. Saying I'm going to filter on this first name based on this thing. Again, it's going to, and it's estimating, well, there's probably 42 that match that. Clearly, there's not. Again, as we said, this is where the estimation can differ from what actually happens sometimes. And then we're going to return the result. Right, so if I were to change this to a profile, just to, again, show you the difference. Right, so now we see what actually happened. Node by label scan, we see exactly what the impact of this was, right? So it still did the same thing. It still said find all of the nodes that are customers. This can tell you again how much memory it took, how many page cache hits or misses there were. So how many estimated rows? So estimated 847, actually 848 database hits. And then the filtering, right? So it hit the database over 4,000 times to do the filtering to get one result, and then it produced the result. Right? So why is this a problem? Well, this is a problem because if I have a million or 40 million or 100 million customers in production at scale, going and getting 100 million customers in the database and then looking through all of those customers to see is the first name what I want would never scale. Right? That would take an extremely long time to do. And so if we deployed this in production, this would be a problematic query. And if we didn't test or scale, we would, or look at it in this particular way, we wouldn't know, right? So what can we do about that? Well, let's take a look at a similar query, but so here's a similar query, right? This is essentially, we're asking the same thing, find customers, we're just filtering on a different property. Yes, one is a string, one is an integer. That's not important, doesn't make any actual functional difference. This is a good query. Let's look at the difference in the explain. So we're going to run this. Now, let's see here. What am I? Okay, so still doing nobody leaves. Okay, so actually we have, let me show you a little trick here. So let's do, it always happens when you do it, show. Because I made a mistake. I made a mistake. So I prepped for this, and then I went ahead and I changed something just now when we were live, of course. And when I did that, I have messed up my own demo. So let me do something really quick right here. See the dangers of doing anything live, and I found they're actually streamed. It's even worse, right? My goodness. So I'll explain what I did in just a moment. That was not what I wanted you to see. It's okay though. We're going to come back. We're going to do that all again in a second. It actually kind of makes for an interesting demo as well. I'm going to run the explain again. Okay, so let's look at this now. This actually works out pretty well. Because we're going to see here, just as before, I was looking for first name. It was doing that node by label scan, right? Go and get all of the customers that exist in the database and then filter on those. Here, let's make it larger again. It's not doing that. It's doing this node index seek. And it says, oh, okay. I want to find all customers by this CID property where the CID is of some value, right? But it's going to do it out of index, and then we go straight to producing a result. This is obviously much, much faster. So as you could probably have guessed at this point, what had happened is I did not have an index on this CID property of customer before. A moment ago, you saw me very quickly use a tool to create that. I could have done it here in the Cypher console. That's more typing. I was likely to screw that up. So I used a tool to do that. But with that index now, the database can very, very quickly look up all customers whose CID is that value and directly return them. So if I take this explain to a profile, right, we can see, yeah, two rows, very, very small footprint, right? 72 bytes, 6 hits of the page cache, 136 total. Whereas again, if we looked at something that was similar before, so again, even without the same query, without the index, far more information, estimated rows, and so forth. And we look at what's essentially the same query, just with a different property type. We get 1,400 page cache misses there. Taking up a bit more memory as well. It's significantly, same memory reducer. It's still the same thing we're producing, but significantly more work being done, right? So again, this index is critical. So the rule essentially there is, of course, a couple of things. One, right, test the queries, learn to use the profile or the explain tool of Neo to understand how that query is going to be run. And if it's slow, the first thing to look at is, are things indexed? But to understand that a little bit better, we have to have a little bit more of an understanding of, at a high level, how does the graph database plan the query? This is at a very, very high level. Okay, so let me go back to this picture that I had here. Let me make this a little bit smaller so we can see everything. Okay, so this explanation of how the database is planning the query is very high level, right? It is not meant to represent the details of how cipher planning is done, for example. That's a very complex topic in optimization, so forth, but a general idea. So when we ask the database to find, for example, all customers, there's a couple of ways you can do that. You can do the first thing I said, which is grab all of the things of a certain label. In Neo, labels are indexed by default. So whenever you create a node with a label, that is automatically indexed for you. You don't have to worry about that, which is why I can do that node by label scan. And so the first thing you can always do is just go and grab all the things of type and essentially pull them off of disk or out of the page cache, look at them, and look at that property to see if it's the right thing, throw away the ones that aren't, and just sort of go through. And that's what we saw without that. Alternatively, again, the better way is to use an index. So index is typically constant time lookup for a property. And you can go get that directly, and then that gives us the node we're interested in. The example we just showed you obviously was trivial. We were just looking for one specific thing. We weren't walking in relationships or anything. Generally speaking, in a more complex query, I'll demonstrate something very slightly more complex in a moment. The database is going to follow the pattern of look at the query, so parse the query, and then try to figure out which node or set of nodes do I use to start walking out the relationships that you've defined in your pattern. And that first step is really, really important, right? That's where you want the database to be able to use an index or indexes so that it doesn't have to go and look at like all of the customers that exist or all of the transactions that exist. You want the graph database to be very as narrow as possible of a set of nodes from which to start walking out those relationships. Because graph databases are really, really good at walking lots of relationships really, really quickly to allow us to find patterns and links and so forth. But if we don't start, we don't give it a good starting point, it takes a long time to figure out which customer to start from, then things aren't going to go well. So if I go back to here, and I have this query, well, that's not the query I want. Here we go. That's the tab we want. So I'm going to, similar to last one, but I'm going to walk things out, right? So find customers that have an email, which is email, where the first name is Clark, and then I want the email address. So if I run that, again, because there is no index on first name, it grabs all of the customers, filters them, and then it walks them. It says, okay, now they know, now I can expand. So I'm going to expand that relationship of has email. It can do that really, really quickly, and then pull back my results. So it does just like we said we can do. Figure out where do I start walking that relationship, walk the relationship. If I turn this into C dot CID equals 282, then again we see much, much faster, grab that one customer, then walk it out. So use indexes as appropriate to allow the database to easily find that starting point. Like anything else in the world, of course, there is a trade-off. The creation of indexes takes time to do during data loading, and it does take up space on disk. So what I typically tell people is if this is if you've got a lot of data, and if you look at that query and you think, wow, this thing I want to filter on is probably going to be a good spot, like for the database to figure out where to start. You probably want to index on that, right? So for example, let's say I have 10 million customers and half of them are male and half of them are female. And I'm never just going to query for gender. I'm never just going to say find me a customer that's male or find me a customer that's female or non-binary or however many different gender expressions I want to include. But it's just imagine that they're all in even number in my database. But I'm never going to look just for that. I'm always going to say, I want to find a customer whose gender is non-binary and whose age is within this range, for example. Um, well, I probably have a lot fewer customers that are in a very small age range in this example than I do of this equally segmented population by gender expression. So age would probably be something really, really good for me to put an index on, so I can get a very small database can very quickly find a small number of customers that match that age criteria and filter them as well. Now, if I'm going to use gender a lot in these queries, I can also put an index on gender, and Neo can use both of those indexes together to make that even faster. But again, it's something you have to play with a little bit and look at, but indexes, definitely your friend. So I'm running a little bit over time, and I want to show you a couple of other things pretty quickly. The other type of is modeling. Modeling, of course, can make a big difference in your performance. And let me move this around a little bit so we can see things. So let's just say this model really accurately represents my retail business, right? This is really how I think about the data. This is how it exists at the high level. Customers have these phones and emails, and they live at places, and they make transactions, right? That's like a receipt, and then the receipt, I have line items, and each line item talks about the quantity of, things that are purchased and what the a dollar value of that was, and that references the product that I bought. So I bought on a transaction which happens on a certain date and has an ID. I have one line item, and that is for 2 pens at 65 cents a piece, for example. And that's very representative of my data, and that's great. I need all that information to do analytics on, so on. Well, maybe in production, I have a scenario where I really need to do a lot of analysis just on customers who purchased certain products. And maybe I'm filtering by a variety of customer demographic info, a variety of product information like product category, product color, product size, price, et cetera, et cetera. All information is in product. Well, I can certainly do those analytics now, right? I can write a query where I find customers that match my criteria who make transactions where the transaction has a line item, and the line item references a product who's also meets my criteria. And the database will figure out, in that case, whether it's better to start at customer and then try to walk out towards products and then filter down the products that match my criteria, or whether it's better to actually start at product, because it believes that's a smaller set of things based on the criteria I've given it in my query, so maybe based on size and brand, and then walk back up to customer and filter that way. But either way, I've got to walk 3 hops. That's not a big deal. Like I said, graph databases are really good at doing this kind of a thing. And this is a fairly trivial example. But again, if I've got a billion if I've got a billion, let's say I've got 500 million transactions in my database, transactions alone, just this path, and each of those may have several line items, which go to different products. That's potentially an awful lot of relationships to walk. So what I might do in that case for scale is I might create a relationship directly from customer to product. I'm going to call it bought product here. So that now for those analytics where I don't care about the date of the transaction, so when they bought it, I don't care about how much they paid for it. So I don't care about the other things that were purchased with it. So I'm not doing like a basket analysis. All I care about is that at some point in time, they purchased this product. So maybe I'm doing a I might be doing some kind of a pass at a recommendation engine. People who bought this product also bought other products. Um, Creating this direct relationship now lets me query for customers who bought products and filter in both those at scale, much, much faster potentially. Again, locally, a couple thousand things. This optimization isn't worth anything, right? I'm going to be writing more data to disk. When I load data, there's going to be some more complexity and some time there to create this relationship potentially. But in those scenarios where I don't need this valid and important information, I just need this, and I might be walking these things hundreds of millions of relationships or more. This can save a massive amount of time. So uh, don't be afraid to look at your model. And even though, again, this path is maybe the first thing we came up with, because that's really how the business thinks about transactions and purchases, to also realize that, oh, well, there is a use case that essentially is shortcutting this, right? This is still a valid relationship. I'm not I'm not creating a rich that doesn't exist. I'm not saying, I'm not inventing some sort of new data. I'm really just shortcutting a path. And I need to do that for a specific use case. Those are things you can definitely look out for here. Other thing I want to say is, and this really applies to all databases, don't feel like you're obligated to do everything in the database. I know there can be a desire to write the coolest, most efficient, most awesome query ever and completely astound your coworkers with the pure amazingness of your query and just kind of like drop it in and watch them, cower before your cipher. Um, and that's cool. You can, and that's certainly can be fun. Uh, but there are definitely problems where breaking them down into multiple queries, potentially even doing some intermediate processing, not in the database, can make things go so much faster, right? I, yes, in many cases, I can do a very complex query where I'm doing subqueries and building up a result and building up a result, and I return the entire thing all wrapped up in a bow. And that's great. And again, it works locally in a small database because I'm only building up 200 things in my subquery and then I'm whittling them back down after I do some math and so on. But if in my production database, I'm building up 100,000, a million transactions, 2 million line items in that subquery, for example, that's eating into memory. That's eating into resources. That very likely may not go well. Don't be afraid. Don't be ashamed to say, I'm going to do step one. I'm going to take what was eventually that subquery, and I'm just going to return that. And then maybe I'm going to step through that subquery and start pulling in partial results and doing that. So definitely, be willing to break down big complex queries, particularly when they're going to happen at scale, into smaller ones. Use whatever intermediate software processing tool you're using to break those down. And then just lastly, let me just give us a new model. I would say a key thing, and we could do a whole show on this, is model the data like you're working in a graph. It's not like, and this again, I've seen this over the years with every database out there. Whenever you move to a new type of database, you move from relational to columnar to document to graph, you have to think about the data in a new way. If I try to take my columnar data and model that like it's, or rather take my relational database and try to model that with columnar thinking, that's going to go badly, right? If I try to look at my graph database and model it like a relational database, that's going to go badly. What do I mean? Let's look at the canonical example, right? Or I have a person and I have a project, right? So people work on projects, right? So the canonical example. If this was a relational database, then I'd be like, okay, person works on a project, and we'll just really quickly say a person has an employee ID. And that's how I know who you are. And a project has a project name. That's how I know a project it is. And if I'm going to track, a person, of course, can work on multiple projects that have multiple people working for them. I would say, okay, right. So if I want to know how this works, that project, I need to have the person, and you have that employee ID in here as well, right? So I know what employee is working on the project. Um, and you can do this, but that's a construct of relational thinking. And I see this all the time. People want to do this. How do I know the person works on this project? Oh, that project's going to know its employees well. Um, really important to look for this kind of thing. When you see duplicated information, in this case here, employee ID, across multiple nodes in your graph model, that's potentially a very strong indicator that you're not modeling this correctly, right? I don't need that here to know this person works in this project. Why? Because that relationship is actually a thing that physically exists in the graph database, and that fact that this employee's ID in working on this project is encoded in this actual relationship that exists in the database. It's not a phantom construct that we just drew that really means, well, that data lives over here in project, like essentially exists in relational databases. Obviously, when we load the data, that data must exist for us to make this connection. But it doesn't. It should not be over here in project. That will lead to excess data in your database at scale. So that's going to lead to problems. And additionally, it's going to lead to um, challenges you may not see until scale in terms of how data starts relating, right? Because this model isn't really right anymore, and you may not see the results of that until you've got enough data in there to hit those use cases, and now you're going to run into problems. So um, that's a big modeling gotcha. It's very, very common. It's the number one thing I see people do is it coming from relational over to graph, and it takes a while to get out of that. And then lastly, I say just be aware what the graph database is good at again. It's really good at walking relationships very, very quickly. If that's what you need to do, graph's a great way to do it. If what you need to do is a lot of math on essentially rows of numbers, probably not your best bet. If you always need to look at the entire graph, that's harder. I would have said it 2 years ago for sure. I would have said no, don't use a graph database. Graph databases are really, really good at starting at one or a handful of nodes and walking out those relationships super, super fast at those. Can't beat it. But if I need to look at a good chunk of the graph, most of, maybe the entire graph, to do analysis, that can be problematic. The Apache Spark X project is designed to deal with that. I am not as willing to say that any longer. In particular for Neo, the Neo Graph Data Science Library has done a tremendous job in providing optimized algorithms that do let you look at whole graph problems very, very rapidly. So I would say be cautious of that still, right? If most of your problems involve looking at almost the totality of the graph, be a little more careful. I would strongly recommend looking at the Neo Graph Data Science Library. I'm sure we'll be talking about that in an upcoming show. But again, if your problems are more like, hey, it's a call center and a customer contacts me and I need to very quickly look at that customer and all of the history of their transactions, all of their shipping history, all of their purchases, all of their previous calls, that entire web of data on that customer, that is incredibly fast with something like a graph database. So we have gone on over and talked about a whole bunch of stuff here. Hopefully given you a little bit of good information on how to take your graph database and scale it effectively. It can absolutely be done. As always, please go ahead and subscribe. I need to get more followers, please. So if you know people, anyone, if you haven't followed and you're watching, please do follow. check out our webpage. Hit me up on social media as well. I'm C. Ritchie on Twitter. And as always, I'm Clark Ritchie, and I'm the Graph Guy. See you next week.